So electron configurations for ions. We talked about this a little bit. Anions gain electrons. So we're adding electrons to the electron configuration. Cations lose them. It is important when you're removing electrons to do them in the correct order. And this comes back to this business with the transition metals and their valence electrons. So for the aluminum atom, here's its electron configuration. It's a main group cation. You're just going to peel them off in the reverse order of filling. So they filled 3s2, 3p1. As you take them off, you're going to remove them in the reverse order. So let's see if I can do this. What color is this? About that color. So we're going to take this one off. And then we're going to take that one off, and we're going to take this one off. Reverse order of filling. For the main group, they're nice and predictable. For the transition metals, you take the valence electrons off first. That does not correspond to reverse order of filling, but you do it anyway. So for iron, we're going to make an iron 2 ion. Here's its electron configuration. The 3d electrons are higher in energy than the 4s, but you take the 4s electrons off first. Oh, maybe this is like evacuating a hotel that's on fire, and you let the people on the top floors get out first. I don't know. If that works for you, that'd be great. Otherwise. So the Fe2 plus cation is going to lose the 4s electrons. So the 4s is just gone here. After that, you're going to lose one of these 3d electrons. So then you're going to end up with this funny-looking electron configuration for iron 3 plus. Okay, so for transition metals, remove the valence electrons first, and then go in reverse order. Okay, the presence or absence of paired electrons and unpaired electrons affects whether something is magnetic or not. You notice that aluminum is not attracted to a magnet, but steel is. Why? Well, it has to do with unpaired electrons. So paramagnetic means that it will be attracted to a magnetic field. That is, if it has unpaired electrons. So those unpaired electrons, you could think of them as being like little potential magnets. They're going to be attracted to that field. A diamagnetic atom that has all the electrons paired up is actually going to be slightly repelled by a magnetic field. So my husband had a great explanation for this. I'm like, ooh, I like that. Okay, so if you look at a pair of electrons, and you want to bring in another electron. So this electron's coming in, and this can flip upside down or stay right side up. It's still not going to be able to align with this. One is going to be opposite, and one's going to be matched up, and so there's not going to be any attraction here. If you have an unpaired electron, and you've got another electron coming in here, this one can flip. It can rotate, and then they can be paired up. So if there are unpaired electrons, those can flip their spin and be attracted to the magnet. If they are all paired up, it's not going to happen. Okay, so this one, no attraction. So unpaired electrons are attracted. That's called paramagnetic. Diamagnetic, they're all coming in twos. Di means two. Not attracted. Yeah?
Can you explain, because you can magnetize a piece of metal like a nail that normally wouldn't be magnetic or attracted to that?
That's a good question. So when you magnetize a nail, or you get the screwdrivers with magnetic bits, right? And the screw will stick to it. It's like, oh, this is great. I don't have to try to hold it on. I don't have to fish it out of the grate later. That metal, before it was magnetized, would be attracted to a magnet. It would be paramagnetic. It would be attracted to a magnetic field.
Just not very
It's just not going to be magnetic itself. But you can't take something that's diamagnetic and make it into a magnet. So when we magnetize things, we take something that's already paramagnetic and we make it actually magnetic. And I don't know the exact details of how that happens. But
So the one on the left is diamagnetic then? The one that's not?
this is diamagnetic, all paired up. And this is where you have at least one unpaired electron that's paramagnetic. That will be attracted by a magnetic field.
All right, cool.
Yeah. So write the electron configuration and orbital diagram for each ion and predict whether each will be paramagnetic or diamagnetic. So cobalt, we only need to look at the valence electrons because all the core electrons are going to be paired up. So cobalt is coming after argon, right? We got argon. Oh, everything's gotten fat now. I don't know what size I was using. So after argon, cobalt is in row 4. So we're going to have 4s2 and then 3d7.
Yeah, 3%.
So you look at that, and it's really not obvious if there are paired or unpaired electrons. So let's look at the orbital diagram.
Oh, but it's plus 2. So if we lose,
Oh yeah, it is plus 2. So
it would be 3d5.
yeah, so it's plus 2. So that's important. So we need to get rid of, wait, do we get rid of those?
Oh, we can
Do we get rid of the D's? Do we take off 2 of these or those?
It's a transition.
Valence electrons first. Okay, so we're going to get rid of those guys.
Wait, so how would you write out the
Well, you could do that. You could put a 0 there. Or you could erase the whole thing. Okay, so that's the electron configuration. Then for orbital diagram, we don't have any electrons in this 4s. And we've got 7 over here. 1, 2, 3, 4, 5, 6, 7. We have 3 unpaired electrons.
So one of them can flip.
So one or all of them actually can flip so that they can be attracted to the magnetic field. Okay, so this one is paramagnetic. It will be attracted. Well, these aren't gonna flip and be attracted to each other. There's a magnetic field out there, and these are moving charges. Moving charges have their own little magnetic field. And there's the north and there's the south, and so in order for it to be attracted, it has to be lined up right. The 3 that are not paired have the ability to switch around, just like magnets. Take 2 magnets and push them together, and if they're not lined up right, usually one will just kind of flip around, and then they'll stick together. So the unpaired electrons can do that. These can't, because no matter which way it flips, one of them is attracted and one is repelled. And so they're just kind of like, they don't really do anything. They're slightly repelled. Nitrogen, 3 minus. Well, let's start out with its atom. So this will be helium, and then 2s2. Whoops, that's not very nice, 2. 2s2, 2p, 3, right? 5 valence electrons. Negative 3 charge, what does that mean? Add 3 electrons. Okay, so this 3 is going to become a 6. So if we draw the valence orbital diagram for that, we've got 8 electrons. We've got 2 in here, 1, 2, and 1, 2, 3, 4, 5, 6. All of these guys are paired up. They're all coming in twos. This is diamagnetic. It will not be attracted to a magnetic field.
So wouldn't that be considered like neon?
It has the same electron configuration as neon, but it is not neon because it has a different number of protons.
So for it to be whatever, the first, it just has to have one actual line or one.
It only has to have one unpaired electron.
So then the whole thing is just, okay.
And then that ion or atom will be attracted to a magnetic field. Yeah. So looking at ions, let's look at the trend in the size of ions. And this is kind of interesting. Cations are much smaller than neutral atoms. And here we have an illustration showing that. So there's the gray is lithium atom. The dark purple or whatever color that is a lithium ion. The change is huge, right? I mean, that's a big change. It's like half as big. Less than half. This is 152 picometers. This is 60. It's a huge change. Well, let's think about what's happening. Lithium is losing its valence electron. It's got one valence electron in the 2s level, right? And so it's losing the 2, and what's left? The 1s. And now there isn't any shielding on those guys. They're getting the full force of the attractiveness of the nucleus. So you've lost an outer layer, and the effective nuclear charge is larger, and so it just goes whoosh, it sucks in big time. Okay, so you're losing the outer layer. You've got higher effective nuclear charge. Cations are much smaller than the same atom that's neutral. Okay, what do you think anions are? Bigger. Thankfully, they are. They're much larger than neutral atoms. So you've added one or more electrons with no change in the nucleus, and so you get a lower effective nuclear charge, and they're going to spread out. And then, it makes sense. Okay, we're taking electrons away. You would think, well, it's getting smaller. It does. You add electrons, you put more clothes on, you look bigger, right? So there's that trend. Isoelectronic. The prefix iso means the same. So isoelectronic means the same electrons. Isoelectronic ions are ions of different elements. They have different numbers of protons, but they have the same number of electrons. So we talk about an isoelectronic series. So sulfide, chloride, potassium ion, and calcium ion. They all have 18 electrons. But sulfur has 16 protons. It's got 18 electrons because there's a 2- charge. It gained 2 electrons. It did that so that it can have 18 electrons like argon. Okay? So they all have 18 electrons, but the charge on the nucleus is different because there's different numbers of protons. So this calcium ion has 20 protons. Well, the effective nuclear charge is going to be larger, right? So calcium ion should be smaller than potassium. We see this trend. This is the largest, and they're getting smaller. Same number of electrons, but higher nuclear charge. Make sense? Okay, so choose the larger atom or ion from each pair. So that's the second one. Potassium or potassium ion? Which one's bigger? Potassium. Because potassium ion, you make the ion by taking away an electron. And it's intuitive that would make it smaller. So the potassium is larger. Fluorine or fluoride? Fluoride. You're adding an electron. It's intuitive. Adding something is going to make it bigger. Calcium ion or chloride ion? So calcium ion and chloride ion both have 18 electrons. So they both have 18 electrons. They're isoelectronic. Both doesn't have an E at the end. Both have 18 electrons. How many protons in the calcium nucleus? 20 protons, right? And for chlorine? 17. So electrons are the same. Which one is going to be larger? Chloride. Because there's less attractive force in the nucleus. So the chloride is going to be larger. If you can understand the basic idea of Coulomb's law and think about these things, you can reason these things out without just memorizing a whole bunch of things that are like just opposite of each other. Any questions? So how do you make an ion? Well, to make a cation, you have to take an electron away. Do electrons just fall off of atoms? No. You have to pull them off. There's some energy needed to take an electron away. So ionization energy is always positive, meaning you have to put energy into the atom to pull it away. So we can write an ionization equation where we take the element, here we're just using M for a metal, and it's always measured in the gas state. So metal in the gas state plus energy, and this is called ionization energy, IE 1. So this is the first ionization energy, is to pull off the first electron. You pull off one electron and you get M+. Now it has a +1 charge, and then you've got one electron that's, yours to do whatever you want with, I guess. Then there's a second ionization energy. You can take that ion and add the second ionization energy, which is different than the first, and remove a second electron. Now you have a 2+ ion and another electron. You could do it a third, a fourth, a fifth, a sixth time. What do you think is bigger, the first ionization energy or the second one? The second one. Because you already ripped an electron off of this thing. And so when you make the cation, it gets smaller, right? And now it's smaller, you're trying to pull that electron away. It's closer to the nucleus, it's harder. So each ionization energy, 1, 2, 3, 4, 5, goes up. There's a trend in first ionization energy. First ionization energy follows the same trend as atomic radius. So the ionization energy decreases as you're going down a group. As you're going down a group on the periodic table, the atoms are getting larger, right? The electron that you're taking, which is a valence electron, is farther away from the nucleus. It takes less energy to remove it. So as you go down, it gets bigger. As you go across, it's jagged, but there is a trend. As you go across, lithium is larger, neon is smaller. The smaller atom is harder to take the electron away from. Okay? Again, with the Coulomb's law, the force needed is inversely proportional to the radius. Small radius, more force needed to pull it away. Large radius is far away from the nucleus. It's harder. It's easier to pull it away. So here are some trends in ionization energies. And we see ionization energy decreasing as you go down. That's pretty consistent. And generally increasing as you go across. But there's some zigzags in there. Okay, on the basis of periodic trends, determine which element has the higher first ionization energy. So tin or iodine? So we've got tin here, and then there's a couple spaces, and then iodine's over here. They're in the same period. Well, which of those is bigger? Tin's bigger, because as you go across, effective nuclear charge increases and pulls the electrons in. It's harder to take the electron away from a small atom because it's got its electrons really close. So this is going to have the lower ionization energy, the large atom, low ionization energy. The small atom is going to have the lower ionization energy. Here we're asked, the small has the higher. It is confusing, so iodine is higher. Write it out, on the exam. Write it down and then go back and look at it. Make sure that you didn't, have a brain fart like I just did. So calcium or strontium? Well, we got to look at their positions on the periodic table. They're on top of each other. So calcium here, strontium here. We're looking for higher ionization energy. High ionization energy comes from a smaller atom. Which is smaller? Calcium. So calcium, being the smaller atom, has a higher ionization energy. Copper or phosphorus? So here, not copper, carbon. So those are diagonal. So as we go this way, we would predict that carbon is larger than phosphorus. And looking this way, we would predict that carbon is smaller than phosphorus. Well, these guys are really close to each other. Which trend is more important? The going up and down. So we're going to go with this trend being more important. That says that phosphorus is larger, carbon is smaller, smaller atom, higher ionization energy. I don't know about you, but I've got a headache. Okay, fluorine or sulfur? So here we got fluorine, and here we got sulfur. You got to have a periodic table to do this stuff. Well, the trend says going across that fluorine is smaller. The up and down trend says fluorine is smaller. The smaller atom has the larger ionization energy. This is another way to think of it that's not scientific at all. So large family, small family. So a friend of mine has one child. I have 6 children. So think back when they were all a little bit younger, and you go to the fair. Big Fresno fair is going on right now, right? I don't go to the fair because I think it would be a great place to lose a child, right? So one of my children was almost lost at the fair, but we got him back, for better or worse. Anyway, so I go to the fair with my 6 kids, and my friend goes with her 1 kid. Who's it easier to kidnap a child from? The big family, because, I can't look at all of them. That mom has her kid by the hand. I only have 2 hands. I can only hold on to the 2 smallest ones, right? So it'd be a lot easier to take one of mine. That's not a PC, a politically correct example, is it? But you'll remember it. There are exceptions. One of the exceptions that we see is between group 2A and group 3A. As we're going across, we expect that boron would have a larger ionization energy than beryllium because it's smaller. But what's happening is that boron would be losing a 2p electron that is a higher energy and is less stable, and so it's easier to remove than a 2s electron. So let's look at the orbital diagrams for these guys. So for boron, and we're just looking at the valence electrons. So for boron, we've got 3 valence electrons, right? 1, 2, 3. And for beryllium, we've got 2 valence electrons. Oops, didn't want to do that. I'll still draw these guys over here. So this is a 2s orbital and 2p orbital. This 2p orbital is higher in energy than the 2s. That's why it fills after. So when we're ionizing boron, we're taking a higher energy electron than we are for when we're taking one from beryllium. The higher energy orbitals are easier to remove. They're less stable. So boron has a lower ionization energy than we would expect. And we see this again between group 5A and group 6A. So here we've got it all done for us. Here's nitrogen and oxygen. And here are their orbital diagrams. So for nitrogen, we're going to remove one of these unpaired electrons. This is a half-filled subshell. That's got this like bonus thing added on. So in the hotel, there's a little bit of a discount if you've got it exactly half full. Over here, we've got oxygen, and oxygen has these 2 electrons that are having to pair. So even though oxygen is a little smaller than nitrogen, it's easier to remove this electron that is having to pair up than it is to remove one of those. And so we see a glitch there as well. Let's go back to this. And so here's the glitch of boron and beryllium. Beryllium and boron. And then there's the glitch for nitrogen and oxygen. And so we see that same glitch pretty much everywhere. This one, we've got those guys in the middle, but we still see this one is a little higher than that, and higher and lower. Successive ionization energies. So here's sodium. The first ionization energy is 496. The next one is huge. It's almost 10 times as big. Well, what's going on? The first ionization energy is removing the valence electron. The second one, now we're going into the core electrons. It's like, I lost that one electron. Now I look like a noble gas. I'm great. What? You're going to take one of my electrons? But I just got where I wanted to be. It's going to be very, very resistant to that, right? Because you're taking off a core electron. These are much closer to the nucleus. And then the third ionization energy is pretty high also. If we look at magnesium, first ionization energy, okay, 738. Second one is higher because it is harder to remove that second one. And then there's this huge one because the first 2 are removing the valence electrons. The next one is removing a core electron. And it takes a lot of energy to pull out a core electron. So this table. So we see, and they've color-coded it and done a line for you and everything. There's this huge jump from the lavender to the pink or whatever colors those are supposed to be. We see this huge jump. You know, here we're going 738, 1450. Okay, that's about twice as big, and then bam, that's huge. Big hit there. Here we've got 1, 2, they're increasing about 900 or so each, and then bang, huge hit. What's going on? Well, sodium has 1 valence electron. You remove that, not so bad. You go into the core electrons, it's going to cost you. Magnesium has 2 valence electrons. Remove the first 2, not too bad. The third one, premium charge. Aluminum has 3. Remove the first 3, not too bad. The fourth one, bad. So it's when you get to removing the core electrons, after you've removed the valence electrons, then the core is much higher. Yep.
We're not supposed to memorize that whole chart, right?
Oh, no.
Okay.
No, you don't memorize the chart. It is to illustrate a point.